podcast is brought to you by LMU Munich.
Looks even bigger from here. So, well, first of all, I would like to thank the organizers for organizing such a wonderful conference and for inviting me to talk here. I think I never talked in such a beautiful room, actually. So I will be talking about mixed correlators in n equals 4 super Young mills. Let me put this. Over the last years, we have seen a huge progress in the computation of observables in n equals 4 super Young mills. Among others that I am not including, these observables were, for instance, the anomalous dimensions, BPS Wilson loops, the QQ bar potential, and also the ones that will be the focus of this talk, scattering amplitudes, null Wilson loops, and correlation functions. In particular, we also have seen over these last 2-3 years that there are surprising relations among these three, and all that is pointing to the fact that n equals 4 has a very beautiful structure. So the plan for today is to discuss the appearance of dualities relations among these three observables, and then towards the end, I will present a related object that I find interesting. The outline is first I briefly will discuss scattering amplitudes, the duality between scattering amplitudes and Wilson loops. This was done like 4 or 5 years ago, so it's pretty old for string standards. Then I will show how these Wilson loops can be obtained from correlation functions. And then we will discuss a particular class of mixed correlators. And then we will end up with some conclusions. The first observable are scattering amplitudes. Scattering amplitudes are basically answering the question of what happens if you smash particles with momenta k1, k2, k3, etc. They are a large family of on-shell observables. They are on-shell because in this theory we only have massless particles, so these momenta satisfy k squared equals 0, and they encode a lot of the structure of your theory. The motivation to study scattering amplitudes in n equals 4 is that they can teach us about QCD scattering amplitudes, or at least we hope to learn about QCD amplitudes, and indeed they share many common features. But at the same time, they are much, much more tractable. So one can go farther in their computation. And correlation scattering amplitudes in general, we need to compute them as physicists because they are the things that you measure. The second observable are Wilson loops. Given any closed contour in R4, any closed loop on R4 or R1, 3, you can define a non-local gauge invariant operator given by the following formula. So this is basically the line integral of your gauge field along the loop. They are well defined for any loop in 4 dimensions, so they are a very large class of observables, and they are quite important in physics. For instance, they provide an order parameter for confinement. Over the recent years, they have become pretty popular because it turns out that by using localization techniques for supersymmetric theories, you can compute some of them exactly, actually, to all values of the coupling. Now, today, what we will see interesting is that actually a particular class of them that I will introduce just in the next slide is actually equivalent to scattering amplitudes. So the statement, and this statement is true only for planar n equals 4 super Young mills, is that given the scattering amplitude of particles with momenta k1, k2, k3, etc., this amplitude is equivalent to all values of the coupling to the expectation value of a polygonal Wilson loop with edges given by the momenta of the particles undergoing the scattering, K1, K2, K3, etc. Now remember that these particles are massless, so here you will have a null polygonal Wilson loop. Each one of these edges is actually null. Now, this duality is actually very powerful. Like, let's say from a computational point of view, the right-hand side is much, much simpler to compute than the left-hand side. Even I could compute the right-hand side. So it's, something pretty powerful. And it is completely unexpected from a perturbative point of view. You could look at the Lagrangian of your theory, and you never would notice that this duality should be there. This duality was initially conjectured, actually just for MHB amplitudes, but then it was extended to all kinds of amplitudes and proven by these people by using twistor techniques. A new character in these developments is given by correlation functions of gauge invariant local operators. Gauge invariant local operators are of this form, for instance, so the trace of two or more fields of your theory. So here we have a scalar field, here F mu nu, derivatives, etc. Now, correlation functions are actually the natural observables in any conformal field theory. And if you compute all correlation functions, then you could say that you have solved the theory, basically. The simplest correlation functions are the two-point functions, and conformal symmetry fixes the form of two-point functions up to these delta i's that are called anomalous dimensions. Now, it turns out that in planar n equals 4 super-Yang-Mills, one can use integrability in order to solve for these anomalous dimensions to all values of the coupling. So you could say that in planar n equals 4 super-Yang-Mills, this problem has been solved already. On the other hand, 3 points and higher are much, much harder. And those are the ones that we will consider. My own viewpoint on correlation functions will be that actually correlation functions can be seen as an off-shell generalization of scattering amplitudes or null Wilson loops. For instance, they are much richer objects in the sense that they depend on many more cross ratios. If you have a correlation function, let's say at insertion points x1, x2, x3, etc., conformal symmetry tells you that the dependence on these coordinates can only be through these quotients here. And these given 4 points are called the cross ratios. So for instance, given a 6-point correlation function, you can construct 9 cross ratios. So it will be a function of 9 variables. So it's pretty complicated. But a 6-point amplitude or null Wilson loop, in that case, you can construct only 3 cross ratios. So it's a much simpler function. Because the point is that in null Wilson loops, these distances here would be null, but not in a correlation function. So I will come back to a second. Now, if we say that a correlation function is an off-shell generalization of a scattering amplitude or a null Wilson loop, there should be some way, some precise way, in going from here to here. And actually there is. And in order to understand that, we need to understand the structure of divergences of correlation functions. Now, correlation functions are generically finite. However, they can develop divergences if you take certain limits. For instance, given a correlation function, you can consider a limit in which point 1 approaches point 2, and there you get the usual OPE divergences. You could do something a little bit different too, and consider, if you are in Minkowski spacetime, you can consider a limit in which the distance between 1 and 2 becomes null. So 1 and 2 are not coincident, but they are null separated. And in that case, you obtain what people call the Lycon OPE. And this has many applications, which I won't mention. Now, there is an interesting limit that we can consider, which is a generalization of this Lycon OPE, and it's the following. We could start from a correlation function defined in x1, with insertion points at x1, x2, x3, etc. We choose an order. We say that this is the first point, this is the second, this is the third, and so on. And we can consider a limit in which this distance becomes null, this distance becomes null, this distance becomes null. So all the consecutive distances become null, all at the same rate. And it turns out that in such limit, so this is the limit in distances, correlation functions reproduce the null Wilson loops that I mentioned in the previous slide. This may be a little bit surprising, so let me be more precise. So what I am saying is the following. You could consider a correlation function O at x1 O n, where each local operator is of this form, so it's the trace of phi squared, where phi is a real scalar in the adjoint representation, let's say of SUN, a group SUN. Then you can consider this sequential null limit that I consider here. Now, already in the free theory, this correlation function will develop a divergence. This divergence is simply given by 1 over the square of consecutive distances, right? Because you have that term. When you do weak contractions, this is one of the terms. You will have also subleading terms, but actually we are dropping them. So we are just keeping this leading piece. Now, this is in the free theory. What happens in an interacting theory is that we have also a finite correction because this scalar field is charged under the gauge group. So since the scalar field is color charged, we get a finite correction, and it turns out that this finite correction in this like limit can be well approximated by a Wilson loop. And here, this Wilson loop is a Wilson loop defined on a polygonal null path of n edges with cusps at the limiting positions. So it's basically this Wilson loop here. This, well, I guess to half the audience will look a little surprising and to other half will look obvious, but it's actually, it can be very well understood in a very intuitive way. So, and the physical intuitive reason to understand that is the following. So consider gxy, the scalar propagator from x to y. Then in the free theory, you know that this scalar propagator is simply the usual factor of 1 over x minus 1 squared. Now you could consider the propagator in the first quantized formalism, and then that propagator is simply given by the sum over paths from x to y. This is in the word line formalism. Now, in the interacting theory, since the particle, the scalar particle, is charged under the gauge group, the particle can interact with the gauge field. And that means that each path acquires a factor given by the exponential of the line integral of the gauge field along the path. Actually, this is just the definition of a Wilson line for a scalar particle moving in external gauge field. Now, the nice thing is that in the null limit, so where the distance between x and y becomes null, this scalar particle is moving very fast, and you can approximate this by using a saddle point approximation. And the saddle point is simply the classical trajectory, which is a straight line between x and y. And you obtain this very simple factor, where this Wilson line here goes straight from X to Y. Now repeating this procedure here for each of the edges in the Wilson loop, you obtain precisely this factor here. So this is actually pretty simple to understand. The details are a little hard, so, and I won't enter into those details. Privately we can talk, but the general idea is actually pretty simple. So the final claim is that if you start with a correlation function and then you take this sequential null limit, then you end up with the usual null polygonal Wilson loop. In this case, in the joint representation, because the scalar field I started with was in the joint representation. I have n equals 4 in mind somehow. Here I have divided by the 3-level amplitude because I want to get rid of this factor. By the 3-level correlation function because I want to get rid of this factor here. So we have this equality. Notice actually that in all what I said, I never used that the theory was planar. I never used that the theory was n equals 4 supersymmetric. So actually this is valid for a generic conformal field theory in any dimension. So it's a pretty simple but powerful statement. Now, it turns out that for the case of n equals 4 super Yang-Mills, one can go a little further and generalize the same limit for other fields that include fermions as well, for other local operators which include fermions as well. Now, this, simple as it is a new tool to understand correlation functions. So, for instance, if you know a correlation function, you can take this null limit and you can recover a Wilson loop. But more importantly, if you know a Wilson loop, this could give you a non-trivial constraint on correlation functions. And actually, this has been used in order to obtain new results for 4-point correlation functions. So it is pretty powerful. Also, from a conceptual point of view, it leads to a triality of dualities valid for planar n equals 4 super Yang-Mills, and the triality looks as follows. So we have seen at the beginning that scattering amplitudes are actually dual to polygonal null Wilson loops. And we have seen that null Wilson loops can be obtained as a limit of correlation functions. So one would expect an arrow here as well, and this is indeed the case, and it was established by these people there. So we have this very nice set of dualities in n equals 4 planar, n equals 4 super Yang-Mills. Now, actually going back to our null limits, one could do something a little bit more general, and instead of taking this sequential null limit of all the local operators of your correlation, you can choose only, let's say, n minus 1 of them, or you could start with a n plus 1 correlation function and take the like limit on only n of them, and this will lead directly to a correlation function of a null Wilson loop with a local operator. So this is, I think, a pretty interesting quantity. You could also do some things a little bit fancier, like, for instance, dividing the insertion points in 2 groups, taking the null limit here, the null limit here, and that would give you a correlation function of 2 Wilson loops. But I don't have time to go into that. So we see that naturally we end up with this object here, which is a mixed correlator of a null Wilson loop with a local operator. So it's this object here. Now, in general, these correlators of Wilson loops with operators, they are pretty important because they characterize what is called the usual OPE for Wilson loops, namely the expansion of a Wilson loop in terms of local operators. Now, for the particular case of null Wilson loops, these are actually very good observables because, well, first we have seen that they interpolate between a correlation function and a scattering amplitude. Then they turn out to be finite, and that I didn't tell you that the other guys were not finite, so it's not surprising for you. But actually, if you compute the numerator here, this suffers from ultraviolet divergences, and you need to introduce a regulator, etc. And the same is true for the denominator. But actually, this ratio turns out to be finite. So you may hope to compute this directly in 4 dimensions. And people not working in string theory, they seem to like 4 dimensions for some reason. So they are pretty good. And finally, they exhibit in a nice way the conformal symmetries of correlation functions. So for instance, we can focus in the simplest case. So the simplest case corresponds to a correlation function of a 4-Casped-Wilson loop. So here you put n equals 4 and a local operator. It turns out that in that case, you can construct only one cross ratio. The cross ratio is given by this combination. Here x1, x2, x3, and x4 are the location of the cusps of your null Wilson loop, and y is the location of your local operator. The fact that you can construct only one cross ratio means that conformal symmetry implies that this object here depends on a single variable. So it is completely fixed up to an arbitrary function of f of zeta. This f of zeta will depend, well, on this cross ratio and also on the coupling constant. So they are very nice. It is a very nice object because it's finite and it's just a non-trivial function of one variable only. Now the question, in a DSCFT you want to compute things at all values of the coupling. So can we compute this f of zeta to all values of the coupling? And I think the answer should be yes, maybe in a few months, but for now let's compute it just at weak and at a strong coupling. I will show you very briefly how to compute it. So at weak coupling, we use the method of Lagrangian insertions. This method actually relies on the very simple observation that if you take any correlator and you take derivatives with respect to the coupling constant, then this can be written in terms of the same correlator with an additional insertion of your Lagrangian. And then you are supposed to integrate over the insertion point. This is actually a very powerful method because it allows you to earn an order in perturbation theory. And actually, if you repeat this procedure many times, you see that if you want to compute loop corrections to the left-hand side, all you need to know is this object here with an arbitrary number of insertions, 1, 2, 3, etc., but at tree level, only at the leading order in perturbation theory. So once you have that, you could integrate over the insertion points, and you have the loop corrections that you wanted. Now, it is not easy, actually, to compute these guys, and they are not known in general. But recently, Eden, Heslop, Korczynski, and Sokachev have computed many of these in order to do a very similar computation, a related computation, that is the correlation function of 4, stress tensor multiplets. So we can take the results, take our partial null limit, and try to perform the integrals. And that will give us this f of zeta at weak coupling. So we did that, and what we obtained was this. So basically, it's a little bit confusing, but let me explain you briefly. So at leading order, we get something very simple, and we get basically 1. Well, actually, the answer is -1, but it's just that. Then at one loop, which is of order lambda squared, so it's a little bit confusing, the terminology, but it's the first non-trivial term, you get 5 box functions. This is the massless box function, and this is the so-called two-mass hard box function. And then at order lambda cube, you get 49 integrals, but I only included the first 4 of them. A nice feature of this result is actually that even though each of these integrals is divergent, this combination is finite. And we have checked this for this and also for these 49 integrals. So you get 49 integrals. Here, for instance, if you use dimensional regularization, you have poles that go with 1 over epsilon squared, 1 over epsilon cubed, etc. All of them cancel, and this combination is actually finite, which is expected but highly non-trivial if you look at the integrals. And actually, the first integrals here are easy enough to allow a computation, and we are able to compute, and this is the result for f of zeta at weak coupling, when lambda is small. At a strong coupling, so this is one end of the function we want to compute at all values of the coupling. At a strong coupling, the technology is completely different, and what we use is the ADS-CFT duality. Then, in that case, we have two ingredients. On one hand, you need the classical solution, the minimal surface corresponding to your Wilson loop, and then a particular propagator from X to the worldsheet. And then you need to integrate over the worldsheet point. Now, for the case of the four-edged Wilson loop, we know all the ingredients, and we have computed f of zeta, and we obtained this. So basically, this f of zeta is this result here at weak coupling, and this result here at a strong coupling. And now we would like to interpolate between weak and strong coupling, probably using integrability. Well, I don't have more time, so actually I will come to a conclusion. So we have seen that in planar n equals 4 super Young mills, there are very unexpected relations between a lot of observables, namely correlation functions, amplitudes, Wilson loops, and also mixed correlators. And these dualities are actually very powerful from a conceptual point of view, because they hint at new symmetries, etc., but also computationally. We have also introduced a new observable. Well, it's not a new, it's a new version of an old observable, which is finite and a function of a single variable, so I think it's an ideal quantity to try to interpolate between from weak to strong coupling. Now, there are natural questions that one can ask. So, for instance, does any of this structure extend to other theories? Well, we have seen that, for instance, some of it does, but it's not very clear. Now, can we compute these correlations here, for instance, these mixed correlators, using integrability? An easier question would be whether you can compute these at a strong coupling for n bigger than 4. Remember that one of the ingredients of the strong coupling computation was that you needed to know the minimal surface of your Wilson loop. One of the problems, one of the obstacles, is that actually for n bigger than 4, you don't know the minimal surfaces. You know the area, but you don't know the minimal surfaces. However, well, recently, Lukyanov, Samologikov, and then Gayotto, Muraniski have shown that one could write TVA equations that would give this surface. So maybe one could use these TVA equations to compute these quantities at a strong coupling. Thank you very much.
You mentioned that this correspondence between the scattering amplitude and the expectation value of Wilson loop only holds for the supersymmetric Young-Mills theory. But it's a bit weird, because actually Wilson loop argument is very intuitive. So why can't you repeat Wilson loop argument for other theories?
No, actually, well, I mean, there are several dualities that they have shown. Actually, let me tell you something. So the first duality is this duality here. That's the one you meant, right? So here actually it is known that scattering amplitudes in pretty generality have some infrared divergency structure that is controlled by the so-called Kasp anomalous dimension. And actually Wilson loops have, well, they are UV divergences, but the structure is more or less the same. So you can match the divergent parts of both calculations. But what is nice and this works only for planar n equals 4 super Jenny Mills, is that the finite pieces of the two computations are also the same. And that is, there you need planar n equals 4 for this part of the computation to work. I mean, these are also pretty complicated expressions. I don't know if people know them for many general theories to many loop orders. So I guess it's hard. On the other hand, the other conjecture I showed, this should be more general. And this doesn't need n equals 4 symmetry. And in that case, you're right. So I don't know if that is more confusing, but yeah. But this you expect to work only for n equals 4 and planar. Yes.
Okay, I don't know how you guessed it, but you just answered my question about the finite pieces. This was my question.
Yes, so exactly, that is the...
Only the singular or also the...
Also the finite pieces. Yeah, so in a way you could have expected that the singular pieces would match, because both of them are controlled by the Kasp anomalous dimension. Absolutely. But what is surprising is that even the finite pieces work. And people have tested this. And actually, well, it has been proven by these techniques, but it's a little mathematical proof. But, yeah.
Any other questions?
You had this nice triangle of dualities in the n equals 4 language, and I was wondering if the gravity dual triangle is understood, in particular the amplitude node and the arrows.
Yeah, that's a very good question, actually. Now, actually, let me tell you a little bit more about this triangle. Actually, the interesting part of this triangle are the arrows rather than the pictures. So now here, this arrow was actually first seen at a strong coupling. And this is something that was first seen in the gravity side of the correspondence. And then people started checking that it was also true at weak coupling. So this arrow here is kind of very well understood in the gravity dual. On the other hand, this one here, the proof we have done should be independent of the coupling, but it's actually a perturbative proof. And I think it's an open problem to try to understand some gravity proof of that. The reason is that there are some expressions for 4-point correlation functions at a strong coupling, but those expressions are valid for generic locations of the insertion points and not for the null limits. That is the one we would need. In the null limit, you would have extra things, and supergravity wouldn't be enough, because you should recover. So this one is not known, actually, how to do it at a strong coupling. And the same happens with this one. This actually arrow here is a proof order by order in perturbation theory. So basically, Nima Cachazo and collaborators, they have, with this Grassmannian, etc., they have some integral expressions for scattering amplitudes at any loop order. And by using the insertion procedure, you can also get integrands for this right-hand side. And these people have seen that the integrands coincide. So order by order in perturbation theory, these correlation functions in the null limit and scattering amplitudes have the same integrands. Of course, then you would have to regularize, etc., but already the integrands are the same. So in a way, it's very perturbative. So it's like, really perturbative, because you still need to integrate. So something at a strong coupling is missing here as well. Yeah.